Well, good afternoon, everyone. It's my pleasure to introduce Dr. Alireza Nojeh, who is an associate professor of electrical and computer engineering at the University of British Columbia. Dr. Nojeh received his BS and MS degrees in electrical engineering from Sharif University of Technology in Tehran, Iran. His work there focused on optoelectronic modulators based on interface charge layers. He went on to receive a DEA degree in electronics, optoelectronics from l'Université de Paris Sud in Orsay and Paris, where he worked on high electron mobility transistors, and he got his PhD degree in electrical engineering from Stanford University in California. At Stanford, he worked on carbon nanotubes, focusing on nanoscale electron emitters. He then joined the University of British Columbia, where he's currently an associate professor of electrical and computer engineering, and his research interests are in nanotechnology, in particular carbon nanotube devices, interaction of light with nanostructures, electron sources, vacuum electronics, and electron microscopy. He also has interests in solid-state electronics, micro-nanofabrication, and modeling and simulation of nanoscale structures. Dr. Nojeh has a lot of talents, including the ability to speak in 3 languages, so you can ask your questions in English, French, or Farsi. Dr. Nojeh.
Thank you very much, Arthur, for the kind introduction. And let me start by thank you all for coming here, and of course, thanking the Institute for this, being so nice as to host me here, especially Arthur and John, whom I don't know where he is, but anyway, thank you, John, and Caroline for organizing this, and everyone who has been taking the time to meet with me. It's a great pleasure and honor to be here. And I know it's right after lunch, so you guys probably had better things to do, if not taking a nap. So I hope I'll be able to make this worth your while. Let me also thank the funding agencies, the people who convinced the Canadian taxpayer to fund our research. Obviously, without this, we wouldn't be able to do this kind of thing. And of course, the real heroes behind this work, my past and present student. Now, I won't be talking about everything that all of these guys have been doing. The things that I'll be talking about today are mostly the works of Parham Yagoubi and Mehran Wahdani Muqaddam, and also to some degree Mario Michan. And if there's time, which quite possibly there won't be, but the sort of second half of the talk, if we get there, a lot of it is the work of Kausar Alam. So anyway, with the important stuff out of the way, now we can sort of relax and talk a little bit about the technical things. Now, I called this, surprises after 2 decades of research on carbon nanotubes. Carbon nanotubes are one of these areas where whatever you want to do, you feel like it's been done before. And people ask, oh, I've seen people having done that with nanotubes. On the other hand, whatever you try to do, you really see that there's still a lot to be done, and there's so much that we don't understand about them. So I hope to convey one example of such a story today to you, because it was something that took us by surprise, and we found it interesting. And of course, very important element of our work. Again, I won't be talking about everything that these collaborators we have collaborated with on, but certainly I would like to acknowledge them first before I talk about the other things. Okay, so I know many of you guys here are real experts in nanotechnology, and many of you have probably worked with carbon nanotubes. So I will be going through the first few slides very quickly, just to make sure that we are all on the same page. If there's any questions, I'd be happy to elaborate more. So carbon nanotubes, carbon, made out of carbon. Oh, John, I found it. Tube, in the form of a tube, nano, with a diameter on the order of a few nanometers. And you can have a nanotube that has one wall or multiple walls. And these have been of interest for 2 decades now, have very interesting electrical, optical, mechanical, thermal properties, and they're going to save the world. All the problems are going to be addressed by nanotubes. Some of the things that I'll be talking about today will have mainly to do with a combination of their optical and thermal properties. Okay. Now, you can make all sorts of different devices with these structures. You can make devices that have individual nanotubes. So for instance, okay. So one nanotube connected to an electrode, or multiple nanotubes connected to an electrode, or in this case, I don't know if it's visible, but one connected, bridging a gap, suspended over a gap, bridging two electrodes in a sort of transistor type structure. Okay, you can do this kind of thing. You can also make large collections of them. So this is an actual photo of what we call an array of nanotubes, or a nanotube forest, with macroscopic dimensions. So this is a silicon substrate about maybe 1 centimeter across. And so we can see that this is about 5 by 5 by 2 cubic millimeters, approximately. And this is an actual photo. It looks dark. It's a very good absorber of light. People call it the darkest man-made material ever. And of course, if you look closely in an electron microscope, you will see the individual nanotubes overall pretty aligned. And each nanotube in this case is extending for up to about 2 millimeters. So although the diameter is on the order of a few nanometers or tens of nanometers, the length can be in the millimeter or even centimeter range. And one of them, of course, looks like that if you pull it out and look at it. And so this is the type of structure that I'll be focusing on for the next little while. How do we make these? Pretty standard cleanroom stuff. You deposit a layer of catalyst, and you can pattern it using lithography, but you do, e-beam evaporation, for instance. You pattern a thin layer of iron. You can pattern this catalyst in different shapes, and then you put it. Oh, okay. So computer is maybe a little too old. You put it in a high temperature environment. You flow in some gases that have carbon in them, like ethylene and so on. And at high temperature, in the presence of that catalyst, the gases break down, carbon comes out, forms nanotubes. So it's really a chemical process. In this case, chemical vapor deposition is quite common. And you have experts here like Shirley Tang or John Yao who do this kind of work. And this is our homemade nanotube furnace. We make our own, and we sort of keep reiterating, and every student who comes in makes changes to it. So it's been very versatile. And of course, I like the colorful glow of the furnace during growth, so I had to include this picture. And here's a small video of how these grow. So this is a time-lapse video of the nanotubes growing on the silicon substrate. In this case, we also had a cap on top, but that's a minor thing. And of course, when you have the cameraman ready, sort of you want to get the best shot, and of course, they don't grow straight on that occasion. But usually, they look better than this. You can get flatter structures. But just to give you an idea, and this takes about maybe 10, 15 minutes to grow something like this. Now, why am I interested in nanotubes? This has been just over a decade I've been dealing with them. And a lot of the background interest that I have in this has to do with sources of electrons, something that shoots electrons out into vacuum. And why is that good? Well, before we had solid state, we had vacuum electronics, right? And still, if you want to do high speed, high power, that kind of thing, vacuum is really good because electrons move without any scattering, right? And then, of course, there's all sorts of other things like electron microscopy, accelerators, medical imaging, which again John is an expert on, displays, and you can come up with all sorts of creative applications of electron sources. But being an electrical engineer, obviously I like electrons, so there's a lot of motivation, and many of these electron beam systems have advanced a lot over the past century. But the electron sources are still quite old-fashioned. There's a lot of room for getting better electron sources. So a lot of my background interest is trying to get electrons out of a material. And carbon nanotubes have several properties that make them very good candidates for this. One is that they're very strong. The carbon-carbon sp2 bond is very strong. So they can withstand very high currents. They're small, so you could potentially get current out of a small area, which is very good. And one real thing is that because they're such interesting systems, really showing a strong manifestation of quantum effects, you could expect to see very interesting things that maybe you could do new applications with. So there's a combination of things that can motivate research on electron sources using carbon nanotubes. So typically what we do in my lab, we do one of two things. We either shine light on carbon nanotubes and look at what happens in there and how electrons come out, or we shine electrons on them and look at what comes out and what happens. So for instance, secondary electron emission and backscattered electron emission and so on. And so typically our work involves using vacuum equipment, putting your nanotube sample in there, then taking some laser beam, shining it on the sample, and seeing what happens, that kind of thing. So the kind of experiment that I want to discuss today, and of course, I'll just say that, again, you can make a whole lot of different structures. So some of my students work more on the fabrication aspects and so on. But I really want to focus on this experiment today. So if there are questions about fabrications, then I'd be happy to answer. So imagine this nanotube array or forest of these nicely aligned nanotubes. And this is not to scale, so they're a lot taller. So you put these in this vacuum chamber. You have a laser beam coming, going through an optical path, polarizer, lens, that kind of thing. And you hit the nanotube forest from the side. And typically in the experiments I'll be talking about today, we focus this laser to a spot of the order of a couple of hundred microns across, in diameter. So the nanotube forest is about maybe 2 millimeters tall and a few millimeters wide, but the laser is focused on one small spot, in most of the things that I'll be talking about today, not all. And this is basically the exception. These are, I'm going to be showing you things from a little bit of a historic perspective. So I got, so this is sort of the starting point of the things that I'll be talking about today. This is a nanotube forest. In this case, we have been flood illuminating it with a beam of light. So this is not focus, it's just flood illumination. And this beam is a 266 nanometer wavelength UV light, photon energy of 4.66 electron volts. Now, the reason we got this laser was because the work function of nanotubes, like many other materials, is in the range of 4 to 5.5 electron volt. So if you want to get electrons out using the photoelectric effect, you have to have a photon energy that can give enough energy to the electrons to overcome the work function barrier. So you need UV photons on the order of 4 or 5 eV. When we wanted to buy this laser that gives us this UV light, we had the good fortune of having the salesman who was pitching for their product telling us, why do you want to buy a UV laser? Why don't you buy a green laser and then an external frequency doubler to get your UV light? This way you will have access to both the UV light and the green light. And that sounded very, very promising, and we said, why not? So we bought that, and that led to something interesting for us, which I'll be talking about. But this simple experiment is really your basic photoelectric effect, where we have put these photons of 4.66 nanometer eV in energy onto these nanotubes. And what I'm showing here, neglect this part, focus on this part, really the number of electrons that were coming out of the nanotube. So this is sort of the dark current, and this is when you have the photon beam on. So you get a lot of electrons coming out. And this was interesting because there was some previous work where people had done this with a mat of randomly aligned, randomly oriented nanotubes, not aligned. And they had seen a lot less current coming out. So this in itself was interesting that, with changing the structure and the density of this array, you could get more current. But there was no mystery in this. This is the photoelectric effect that Einstein described 100 years ago. Now, since we had the green laser also, because imagine we have this green laser here and then a frequency doubler here, we're using the UV that comes out of the frequency doubler for this. But one day we said, why don't we also try with the green light that comes from the first laser, right? Now, the green light has a wavelength of 532 nanometers, a photon energy of 2.33 eV, right? That's way less than the work function of nanotubes. So we said, of course, if we do this, we won't see anything coming out of the nanotubes. No electrons coming out, but it doesn't hurt to try. Let's try it. We tried, and of course, we saw a very large current coming out of the nanotubes. So that was quite a surprise. Now, you might say, there is another way I could get electrons out. What if my laser is actually heating the nanotubes to a very high temperature, right? You guys know what the thermionic emission effect is. Again, something that's been known for 100 years. So if you heat something, a metal, to 2,000 degrees, electrons will start boiling off. So electrons will come out through the thermionic effect. Could we have that? But we didn't expect any of that. Why? Here's the reason. Imagine you have a conductor. Imagine this is a piece of tungsten, bulk tungsten. And these experiments, like I said, we started focusing the laser. You focus a beam of light onto this piece of tungsten. Of course, you will generate some heat here. But what happens is that the heat spreads to a very wide area, right? Because conductors are good conductors of heat as well. So the result is that you don't get much temperature increase because this is acting as a heat sink. You could heat it up really to high temperatures if you pumped in a lot of power. So if you go to, for instance, an accelerator that uses a copper or tungsten electron emitter using the thermionic effect, you will see that it has a big megawatt pulsed laser that can give enough power to heat this up. But we didn't expect any of these because we were just using a continuous wave laser with a few watts or hundreds of milliwatts of power. So just orders of magnitudes less than this, right? So we had literally months. This is about 2 years ago, almost now. There were months of being puzzled. What's happening here? This certainly can't be photoelectric emission and certainly can't be thermionic emission. What's going on? And eventually we started looking more and more closely. And this is what we saw. That so instead of that bulk metal, if you have this forest of carbon nanotubes, and you focus this beam of light onto here, now remember, nanotubes are excellent conductors of electricity and heat. In fact, people are trying to use this kind of structure for heat sinks. So in this case, we would expect this heat generated here to be dissipated along the direction of these nanotubes to a very wide area, right? So they're good conductors. What we saw when we looked very closely was this, that in fact, no, the heat was localized more or less to the spot where the laser is illuminating the sample. That was, again, quite surprising. How can that be? Isn't it supposed to spread? But this wasn't happening. And you could actually see it. It's quite visually interesting, actually. This is an actual photo where you have the silicon chip. This is the nanotube forest. This is the sidewall of the forest, the nanotubes like this. What I'm showing here is the laser light filtered out. So you don't see the laser light. What you're seeing is a spot approximately the size of the laser light, which is glowing because of its high temperature. Incandescence, black body radiation, right? And you can actually measure this temperature by putting this into a spectrometer and looking at, trying to fit it to Planck's black body radiation law, and it gives you a pretty good fit. And you can tell the temperature. And we've been going up to almost 2,800 degrees with this. So now you might say, why is this? Why do I care about this? Now, first of all, this was interesting. Really, we thought it was cute. Okay, so we tried to understand this a little more. But on the other hand, there's also an interesting implication for this. And it's the fact that, like I said in the beginning, you can't heat a regular conductor to 2,000 degrees with a few watts or a few milliwatts of power, or a few hundreds of milliwatts or a few milliwatts of power. So the practical implication is if we can do this, then we might be able to make electron sources in a way that others haven't been able to make in the past with more conventional materials. So the fact that you can do this with low power is very interesting. And the reason is because the heat is not spreading to a wide area, remains localized, You don't need to put in too much power to heat it up. So the lowest we've ever gone, I don't know how much the power of this laser power is. Okay, maximum output power, it says 5 milliwatts. Okay, the lowest power we've ever tried and gotten this kind of thing is 4 milliwatts. So in theory, if I could focus this with this kind of laser pointer, you could do this. So instead of needing a giant powerful laser, you can do this with a handheld laser. And I will show you some movie of that shortly. But a big aspect of what's happening here was for us to try to understand this. And long story short, this is what we think the mechanism is. And I'd be happy to discuss this more if there are questions. But think about trying to model this problem. The power conservation equation, you've got the laser power in. Now, this power is lost due to three mechanisms. One is due to the emission of electrons out of the nanotube. They carry energy with them. The other one is due to the incandescence, the blackbody radiation, so the energy lost due to re-radiation. And the third one is if you do have any heat transfer to the surrounding areas, power loss due to that. So if you try to write the equation, you can build a simple model for that. And you can do it for a bulk conductor, for instance. You can do it for this quasi-one-dimensional array of nanotubes. And of course, in both cases, you have a lot of similarities. The first two terms are going to be more or less the same. In the third term, you will see a big difference, because in the bulk, heat transfer happens isotropically in all directions. In the nanotube forest, it's more or less along the nanotube direction, axis. So the third term here looks different, okay, for the two. There's also something else that one has to realize, is that, I said thermal conductivity of nanotubes is high, but thermal conductivity at what temperature? Because thermal conductivity, like any other material property, could be a function of temperature. Okay. In fact, for any material, if you go, I don't know if this is visible, but this curve is thermal conductivity as a function of temperature. If you go to really high temperatures, the thermal conductivity drops. Typically as 1 over temperature. And this is basically due to Umklapp type scattering. In nanotubes, there is some reports in the literature where you see this even a faster drop of the nature of 1 over p squared. So it's even a faster drop. And this report is limited to almost 800 degrees C in range of temperature, because it was done in air, and beyond that, nanotubes are destroyed in air. But we sort of assumed the same behavior extending all the way to very high temperatures. So in this third term here, if you put thermal conductivity as a function of temperature also, then you can solve this whole equation and try to find out try to find the temperature out of this equation as a function of input laser power or intensity. And when you solve that, you see that if you do it for a regular bulk, you need intensities on the order of hundreds of kilowatts per square centimeter to start seeing any substantial increase in temperature. Whereas for this nanotube forest, orders of magnitude before that, you all of a sudden have a very nonlinear transition. And so what we think is happening there is this, that once you reach an intensity threshold, a little heat accumulates there. It can't dissipate easily to the surroundings, so temperature goes up a little bit. As a result of that, thermal conductivity drops a little bit, right? And so you enter a snowball effect, a positive feedback mechanism, whereby all of a sudden you go from one semi-stable situation to another one, where all of a sudden the temperature shoots up very significantly. And in fact, we've seen in experiment that this is very nonlinear. Once you start focusing the laser without much power, just reaching that threshold of intensity by focusing a little more, all of a sudden the thing starts glowing and temperature goes up. And for obvious reasons, we call this heat trap, because in this regime and beyond, basically what seems to be happening is that you have quenched the thermal conductivity. Temperature has gone up, thermal conductivity has dropped. So you have this area of thermal sort of isolation with respect to the rest of the nanotubes. and that's why it can heat up so easily. Interestingly, it still maintains significant electrical conductivity, so you can get electrons out of it. And in fact, here I'm showing an example of the electron emission current as a function of laser power, and you see this sort of exponential rise. And that fits the thermionic emission law proposed by Richardson 100 years ago. That fits it pretty well. And, when you do the temperature measurement and electron emission current measurement, you put them in Richardson's equation, and all these fit quite well. So it's clear that there's a dominant electron emission component here that's thermionic, and that temperature is high, and so on. So let me show you how it works. So I was telling you how a laser pointer does this. Here, this is a handheld laser. This one actually costs a couple $100, only a few tens of milliwatts, from a company on the East Coast here. And what I have here is a small glass tube, mini vacuum chamber, which we made so that we could move it around and demo it. And what you see is an aluminum electrode here. On it you have the nanotube forest. Then there is a counter electrode here, which is not connected to the forest. There's a gap between them. Okay, you can't see it very well here, but that's for collecting the electrons that come out. And inside is vacuum. Okay, so when I turn on the laser, by the way, when I say I really mean we, a group, right? Because the people who do this work are it's mostly not myself. So they deserve the real credit. So what I'm showing you here is that you can't see the laser, right? This is an infrared laser in this case. So the glow that you're seeing is really that black body radiation from the hot forest. Now you might say this is not localized, but you have to take my word for it because this is dispersed by the glass. But I showed you an image earlier where with a good high resolution camera you see the local glow. And in fact, same thing, but in this case, we're also looking at applying a little bit of positive voltage to that counter electrode to collect the electrons that come out. So you see that whenever this turns on, you get a good electron emission current out of it. So same exercise as before. Okay. Now, see, I told you that we started doing this with a green light, and it was how we got into this accidentally. But very soon we realized that it's not really that strongly dependent on wavelength, because nanotubes are a good absorber of light in a very broad band. They're very black. And so, like I showed in the previous movie here, in that case it was an infrared light. So here we're looking at how it behaves with different wavelengths in quite a broad range of colors, and it works with UV also, actually. And with relatively similar ranges of power, you will get very similar ranges of electron emission current. And the difference in power is because not all the lasers have the same spot size and can't control it exactly. But so this is not, to the first degree at least, dependent on the wavelength. And here I'm showing a combination. When you put some of these different wavelengths and try to combine them, then you see that it's really just adding the powers that matters, even though the wavelengths are different. If you add two lasers, the current that you get is as if you had the power of the two added in one wavelength, and it increases exponentially. Another thing that's interesting about this is that it's very strongly polarization dependent. If you polarize the light beam such that the electric field is along the direction of the nanotubes, you get a lot more current than if it's perpendicular. And that's somewhat expected, and you can do simulations that back up that observation quite strongly. Okay, but so these are, and this is an ongoing thing for us, to really try to understand the physics of this a little more. Because everything that I told you about, I might be wrong. I mean, this is a model that we've developed. It's a phenomenological model. We don't know exactly what was really happening in there, right? There might be some sort of phonon traffic jam that happens as temperature goes up that quenches thermal conductivity. But there's a lot of room to study those things. But these are some of the outside aspects of it that we're seeing. But now what I want to do is to switch a little bit and put on my true engineer's hat. Okay, and talk about a particular application that we thought might be interesting. Now, you guys are familiar with photovoltaics. Solar cells are very important, of course, and typically you do it by creating a semiconductor junction and shining light, getting electron-hole pairs, and sweeping them away and delivering power to an external circuit. There are other ways that you can use sunlight to generate electricity. So, for instance, you can use a lot of mirrors to concentrate a lot of light on a pot of water and boil it for a steam turbine. There is another way, which about a year ago or so when we were getting these results, we thought we had invented this. But of course, we realized that it had been invented only a century ago. Okay? Like everything else that you invent, it has been done before. So this is called thermionic energy conversion. If you have a hot electrode, electrons will emit thermionically. If you collect them with another electrode, this is, let's say, in vacuum, and then feed them to an external load, you have converted heat to electricity. Earliest paper, I think, 1915, this was proposed. And obviously, for decades, people have been trying to see if they can do this with sunlight, because this has some interesting properties. If you increase the temperature just a little bit, the current goes up exponentially. So potentially, you could go to high efficiency and so on. So one of the prominent players in the field has been NASA, because especially this is vacuum and radiation resistant and durable and simple and lightweight. It's very desirable for things like space applications. But there has been other people interested in it too. So this is all very nice. But remember, if you want to heat something, a conductor, to high temperatures, the heat spreads to a wide area, so you need a lot of power. Sunlight is not typically enough, unless you use this kind of gigantic mirror. Now, I don't know exactly where my student found this picture, so this might not be NASA's picture. But what I want to point out, here's these little human beings here. So this is the amount of sunlight that you really need to focus to create a good amount of heating of a regular metal. But even so, when you do that, this heat has been spread to all over the place. So then you need very good heat shielding to isolate the rest of the device and so on. So the devices end up being very complex structures. So as a result of these two things, this has never become really practical. There has been multiple programs on it, but it's still been at the research level. Nonetheless, really pushing the limits of engineering, 50 years ago, NASA has shown efficiencies that were quite remarkable back then, right? Photovoltaics, I don't think, was competitive with this back then. And in fact, if you look at the theoretical estimates of the efficiency of such devices, they could be upwards of 40%. So it's very promising. But like I said, it wasn't practical. So, for us, when we saw that this is working with low power and it's working with a broad range of wavelengths, we thought, how about another abundant source of light, right? Of course, abundant, not in Vancouver. So you might say, how come the guy from Vancouver is trying this kind of thing? But it was accidental for us, okay. So we thought, let's try it with the sun. Now, it's not trivial, because sunlight and laser have very different properties, right? Coherence, and polarization, and all. We said, let's give it a try. If we can make it work with our small little compact vacuum tube compared to something like this, it might be interesting from an applications point of view. And so, we've done this kind of thing with paper when you were kids, right? Trying to burn sunlight, paper with sunlight and a lens. But the question is, does it work with nanotubes? So every now and then there is a sunny day in Vancouver, not very frequently, but you can find a day when there is enough sun to try this. So this is the courtyard behind our lab. We took this outside and we tried to see if it works with sun. So, you see us with this lens trying to focus, and of course clouds are coming and the sun is shifting. But it's not that challenging. And here you go. What I'm showing here is an actual measurement curve under sunlight, the actual sunlight. And this is the voltage applied to the anode, being swept from positive to negative. Now, what does that mean? Here, these are the nanotubes. This is the voltage source, and we're measuring this current. Now, if I apply positive voltage to this collector or anode, I'm helping the electrons go from the electrons that have been coming out of the nanotubes, I'm helping them to be collected by the anode. And in that case, really, I'm not generating power here. I'm delivering power from this voltage source to this device. And that's what you're seeing here. Okay. But if I apply negative voltage to this anode, now I'm opposing these electrons. And they really have to use their own kinetic energy coming out of the sample to overcome this potential barrier to make it here. And if they do, then they're actually delivering power to the external circuit. And you see that there's quite a range here where you have this power. And eventually, of course, if the voltage is very negative, then you completely stop these electrons. This is the so-called stopping voltage. And this curve, if you want, is very similar to what you see in a photovoltaic device, right? Usually you plot that in this fourth quadrant. In our cases, we plot it in the second quadrant. But it's the power generation regime. So this is actually generating power under sunlight, and it's working. So here's just an electron source, but here's really a solar cell, if you want, a power generator. And you might say, well, there's still a voltage source. I don't like that. If you disconnect this, which we've done, and you put a resistor across this, you will see a good voltage build up across the resistor. So that's very interesting to see. So it's really a power generation device. Now, if you look at the scale here and do the math and calculate the efficiency, you might attack me right away and say this is completely useless, because efficiency is very poor. You know, remember, this is the first prototype without any engineering and so on. The efficiency of this very first prototype, at the best point you calculate, is about 10 to minus 6%. Okay. So the reviewers, of course, were saying this is noise, this is useless, it's not practical. But remember, we are measuring the current with very high accuracy here, on the order of a few tens of picoamps. So this is really not noise. It's actual power delivered. It's very low. But remember, thermionic emission is exponential. So if you manage to heat up the sample a little more, you could improve things dramatically. The first prototype was just using really the first lens that we found lying somewhere on the counter. Then we decided to buy a slightly better lens, $50 this time. And immediately we went up in efficiency by 2 orders of magnitude. Okay, and this tells you, and this was, you know, only a couple of months of playing around with things. So, you know, the improvement, if you want, was quite significant. It's still very low efficiency, but the improvement was significant. And so there is actually a very clear path to improving this efficiency further. When you look at this equation that I showed before, really most of the loss is happening to this black body radiation of light. You want to reduce this and increase electron emission. And if you remember that, this black body emission is a function of the fourth power of temperature, Stefan-Boltzmann law, whereas electron emission is an exponential function. And if you go higher in temperature, you could have this dominate over this one. And here's a simulation that shows that effect, that if you go to really higher temperatures, you can go very high in efficiency. Of course, this is a simplistic model, so it really will end at around 40, 50% here. But so right now we're operating in this kind of regime. So, but the other thing is that if you don't want to go too high in temperature, which you probably don't because you destroy everything, if you manage to reduce the work function of the material, you will see that at much more reasonable temperatures, you can go to very reasonable efficiencies. So there is room for engineering here, and of course, a lot of study on the chemical properties and surface and work function of nanotubes. So that's one direction. But what I want to point out is that, like I said, there is a lot of sort of potential for improvement and engineering this device further. The other thing I want to point out is that even with this low efficiency, which is really negligible at this point, if you look at the current per unit area of the sample, or the power density coming out of that unit area, you will see that it's already, if you look at these numbers and compare with this is from a recent review of photovoltaics. So this is state-of-the-art photovoltaics. You see that the numbers are very comparable with state-of-the-art photovoltaics in terms of power density and current density. And that's something that's very important because it determines cost, right? So even though efficiency is poor, on some of the fronts, it's already quite competitive, even these early prototypes. So this was really an example, I think, to me, that highlights the fact that if you think about the conventional things that we do, the type of research we do in our lab, or the devices that people build, and then you put a nano twist onto it. You use a cathode that very much looks like an unremarkable piece of any other material, but really inside is this nano-structured material with these aligned nanotubes. You will see effects that sometimes allow you to take traditional applications, maybe from something relatively impractical to something potentially practical. So I think it's an example of the hidden or surprising things that nanomaterials have to offer. And in this case, without necessarily setting out to do something specifically about energy conversion, we sort of accidentally came across that. But I guess by sometimes keeping an open mind, one could find things that might be of use at some point. Who knows? So this was an example. And so I think I probably have 5 more minutes. Is that fair? Or 10? 10 more? Excellent. So I'll switch a little bit and talk about another interesting aspect of the same nanotube forest. But before that, just to finish off the discussion on this thermionic emission, like I said, it also works with UV light. Now remember, with UV light, we started doing the photoelectric effect, where the energy of the photons is sufficient to take electrons out of the Fermi level up into vacuum, overcome the work function barrier. On the other hand, we also do see the same heating effect with UV light too. So one thing that's very interesting is that now you can do an experiment where you go from a very wide range of intensity of your light and look at the current that comes out. And you can also you realize that as soon as you go above the heat trap threshold that I mentioned, the temperature also goes up. So now you can measure the current as a function of temperature. But remember that in this case, it's not just thermionic, it's a combination of photoelectric and thermionic effects. So what you're seeing here is a sweep of emission current as a function of temperature under photoelectron emission conditions, under photoelectric conditions. And this was interesting to us because this curve that you're seeing here, you find it in the literature from the 1930s, the so-called Fowler-Dubridge model of photothermionic emission. But it was more of a theoretical curve. And as recently as last year or 2 years ago, you would see the same sort of artist's impression or theoretical version of this curve in papers showing the combined effects of light and heat on electron emission. What I'm showing you here is an experimental example of that, which is happening because you can do this very easy heating with a low-power ultraviolet light, which you don't easily find in the literature, the experimental version of this. So it's very interesting to people who do photoelectron emission like myself. And another thing that's interesting, if you take a very close look, is that this current as a function of laser intensity, if you plot it on log-log scales, you will see a slope of 1 here, and then there's a regime which has a slope of 2. Now, for people who do photo emissions, slope of 2 is important because that indicates a second-order process, a 2-photon photo emission type of process, 2 photons combining energy and kicking out 1 electron. That has been done in a lot of materials, but again, with intensities that are orders of magnitude higher than this. And for this, we just don't have any explanation right now. And our paper on this got rejected yesterday because we didn't have an explanation. So that's fair, I guess. But so this is another interesting aspect of this. But now I want to switch to something else about nanotubes. Something that has been a really interesting collaboration that my colleague initiated, Professor Kenichi Takahata at UBC. He's an expert in MEMS, especially micro-electro-discharge machining, meaning that he has this probe that comes near any material and then creates a localized arc discharge and carves the material, right? So he said, can we try this with the forests? And we tried, and it worked beautifully. So we've been doing this for a couple of years now, trying to do all sorts of things with the forest. And here I'm showing you examples of microchannels of all sorts of shapes and different depths, all done in the same forest after the growth without any pre-patterning. And the remarkable thing is you're not limited to two-dimensional patterning, but you can do angled surfaces, different depths, so completely free-form, three-dimensional. So all sorts of channels, and who knows, maybe use it for fluidics or whatnot. So this was something interesting, and we tried to do, we wanted to pattern the Olympics logo, but they said it's copyrighted, so we showed our support in another way. So this was very interesting. Now, one of the things that his postdoc, Ken's postdoc, one day we were chatting, and he said, I want to bend these nanotubes. Without trying to carve the forest, I just want to bring this tip of this micromachining system that I have. I want to push these nanotubes and see if I can change their direction. I said, sure, that sounds quite interesting. Maybe you can create different directions of channels of heat flow or electron flow or whatnot. So he was doing some of these, and all of a sudden, he noticed that he can see the picture of this tip that he was using to do this in the nanotubes, a mirror reflection of the tip in this otherwise very dark and black material. So, we took a closer look at this and a lot of experiments, and it turns out that by simple mechanical polishing, if you want, you can turn this, what people claim to be the darkest man-made material ever, you can turn it into a mirror. Now, this is not the most reflective. The reflectivity of these first samples have been on the order of 15%. But that's something that, you can see an image in it. And sometimes you can get patterns that look like gratings that will lead to these beautiful diffraction, colorful patterns. So you can make this kind of things, where you have next to each other a super dark material and then something with a very respectable reflectivity. So, he's in MEMS. He tells me that this could be useful for micromirrors, and this is a flexible material. So, I guess what I want to say is that I should probably wrap it up around here. But what I want to say is that with very small differences, the same material can do so many different things. So that's why I say it's full of surprises. And of course, I guess what I'm going to say is that in a few months' time, you guys are going to have a supercomputer that takes its power from the sun, has this localized thermionic generator right here, and does all sorts of fancy computing using these mirrors and optical signals and whatnot. Right? So in a few months, you don't need anything other than nanotubes, and it will take care of all human needs. Okay. So, and people have been saying this for 2 decades now. Okay. So obviously, I'm going to say the same thing too. So I think with that, with electrons and nanotubes, there is some similarly interesting stories. It's again a rich area, but I think probably there isn't enough time to do something meaningful about it. I'll leave it here. I'll end by again thanking you guys very much for coming out and the Institute for hosting this. Thank you very much.
Okay, thank you, Alireza, for that really interesting talk, because if I would have thought that we have done everything we could on carbon nanotube, and people never cease to amaze me and come up with new things to do with it. This is one prime example. On one of the video that you have shown, you have shown a laser that points to a forest of carbon nanotubes, and you generated current. And when you block that current, it seems that the cooling is instantaneous. So just wondering about the time response, because carbon nanotube on one hand, because of this positive feedback we talked about, that create this heat trap. But when you block that light, it seems that it goes in the other direction. It becomes a heat sink. So could you comment on that?
Excellent question, really. So we used a chopper, a mechanical wheel, to chop the laser beam. And up to a few hundred hertz, we saw the signal follow. So very fast, as you pointed out. It seems to cool down very fast also, which is great, because you can now pulse this thing, use it as a pulsed electron source. And we tried to do similar things with a piece of tungsten, for instance, of course using a lot more power and focusing to get the heating. But after a few hertz of chopping, then the heating and cooling doesn't follow anymore. So the cooling seems to be also very fast once you turn off. So exactly as you pointed it out. And very recently, we've been fortunate to be able to get a femtosecond pulsed laser. And as recently as last week, actually, for the first time, we tried it with that, and we still got the effect. But of course, I mean, the actual dynamics would be very different at the femtosecond. But the heating and cooling seem to be remarkably fast, which is yet another surprise. So, excuse me. So one of the things, maybe one could try to make a controllable heat sink out of this, where you can. Yes?
The spot size of the laser, as far as I noticed, the scale of millimeter, right?
The laser is a couple of hundred microns. So the nanotube forest is a few millimeters in dimension, but the laser is a couple of hundred microns, depending on the experiment. But it's smaller than the length of the nanotubes.
Yes, but in the picture I saw, there is like the target zone is a scale, like I'm saying, you're netting the laser in the scale of 1 millimeter, for example, in diameter in the CNT forest, right? It's not smaller. I'm wondering why you didn't try, I don't know, if you have ever tried, like, focus in the smaller zones, like where you have, for example, again, I don't know, if you have tried different configuration of CNT in different distances, interdistance, then you could have like laser targeting in like one line of CNT. Such thing could like simplify the, I know again how you solve the heat transfer equation when you like you said laser source equals to the 3 possible ways of heat dissipation. I know how you solve that if it is analytically solved and like verified by experiment. But I'm saying if you could do in the lower scale, you could have better clarification on the heat transfer.
Yeah, absolutely. Very good point. So the smallest laser spot that we've gone to in diameter is about 50 microns or 100 microns, right? So of course, you could focus lasers to a micron or sub-micron even. It's quite hard. So the optics are very involved. But even if you do that, you're still illuminating a lot more than one nanotube. So in terms of really going to an individual nanotube, you would most probably have to go to some sort of near field technique. Let's say like a tip enhanced, the kind of thing that people do in tip enhanced Raman and that kind of thing. But absolutely, and so that would be an experiment, on our wish list to really look at the temperature profile. And there are people who do this kind of studies also in different contexts, not up to this elevated temperatures, right? But you're absolutely right that would simplify the modeling. Having said that, with this model involving a sort of macroscopic area, if you make a bunch of simplifying assumptions, like assuming that the laser is a perfect circle with uniform illumination, with uniform temperature over the entire spot, all of which are not true, strictly speaking. But if you make these approximations, you can do almost analytical. So you can have a closed form equation that then you can solve numerically, but very, very easily. And the results match the experimental data quite well. So even at this very simplified model level, it already does match the experiments. But you're absolutely right that there's a lot of room for going to the really, really bottom of it.
Or maybe the other orientations of CNT? Like
Yes. So we've done this from the top also, and it works. And so when you change the angle and so on, you do see effects. You change the angle, polarization, you go from the top, but you do see the basic effect. Very similar. Where? Here?
What kind of energy densities are required to enter the heat trap?
Yeah, so the kind of threshold, the actual threshold is dependent on the spot size. But for spot size on the order of 100 microns, let's say, the threshold is about 50 watts per square centimeter. So, if you're at a small spot of 100 micron across, you can do it with a few milliwatts, a few tens of milliwatts. I think we had back here. We'll go.
Is the type of substrate that you grow the carbon nanotubes on, does that have a role?
That's a very good question. We haven't tried this on different substrates yet. This is all on silicon. The spot is quite far from the substrate, as you can see. So one could say maybe it's not dependent, but I can't answer that unless we do it. We haven't.
That's very interesting because you use a polymer like for substrate, flexible substrate.
So, sorry, could you?
Because if you use a polymer-based flexible substrate, and then maybe you can also see the bending effects.
Sure, yeah, very good point. Yeah, absolutely. Yeah. I think we had a question in the back and then.
Excuse me, my question is, so you never consider about the volumetric effect? Because
that's one of the things I was hoping to talk to you about. Because I saw your name and I realized you're one of the authors of one of the papers on this volumetric effect. And that's one of the things that we think maybe could be done with this. Yeah, precisely. Absolutely right.
Hey, this might have been asked before, but like similar, but did you see what kind of effects the trenches would have on your efficiency?
The trench?
The trenches you make into the
Oh, this kind of thing. We haven't done it yet. Yeah, no, we haven't. But absolutely, again, another sort of, it's the thing I was saying with nanotubes, right? You think you're doing one experiment, you will be done, but then now all of a sudden, look at how many great suggestions I'm getting like this one, right? There, Shirley. You're quite right that basically trying to make some sort of photovoltaic device, right, is, I guess the role of the nanotubes is a little different there, but at the end of the day, you're trying to harvest light. So I think the pros and cons, really, because this is so new, I can't comment in a way that maybe really I won't embarrass myself in a year I won't be embarrassed in a year from now. But I'll venture a couple of points. One is the fact that, like I said, this is fundamentally an exponential process, right? And so as opposed to a photovoltaic process, which is linear. So even if you focus a little more, it's at the end the amount of power, not the intensity, right? That tells you how much electron hole you get at the end. So this is exponential. So if you could engineer it well, you could potentially have a faster rate of efficiency improvement compared to a photovoltaic device. Another thing is, like I said, thermionic devices are kind of inherently a little more robust, if you want, because most of it is empty space. Now, if you do a photovoltaic device with nanotubes, it would be obviously just as robust as this. But I'm talking about compared to maybe more traditional photovoltaics. And what you pointed out, trying to separate electrons and holes, basically break down the excitons in nanotubes. That's I guess, a very important area for research. This is just really another parallel area, right? So I wouldn't see these as competing or replacing each other, but basically, maybe one day someone coming up with a way of combining all these things, right? Even, let's say, using some of the light that is being re-radiated by this, right, which is wasted, collecting it by another device, which may be another nanotube-based, but this time photovoltaic device, right, to generate electron-hole pairs, and who knows, right? But the mechanisms are fundamentally different. Pros and cons, really, I think, whichever makes it into a practical application sooner will be more useful from that point of view. Fundamentally, they're both interesting, I think. I hope that answers a little bit.
Any other questions? If not, I hope you'll join me in thanking Dr. Nojeh for a very interesting.
Thank you very much.